to this second tutorial about numbers. If you haven't watched the first tutorial, I would recommend you do that before watching this one. So, numbers continued. So in the last tutorial, we introduced the notion of a number line that would go to minus infinity in this direction and positive infinity in this direction. And we saw that on this number line, first of all, we could represent the integers. So starting with 0, and then positive integers, and so on, and then on the other side of 0, the partners to the positive integers, the negative integers. And so on. We also introduced a set of numbers that we called the rational numbers, which we defined to be those numbers which are a fraction of integers. And we gave some examples. For example, 1/2. We gave an example of top-heavy or improper fractions, such as, I think the example we used was 7/3. And we also talked about negative rational numbers or negative fractions, loosely speaking. I think the example we gave was -3/2. And we just showed how we can easily represent those numbers on the number line. So there's 1/2, there's 7/3, and here would be -3/2. Now, the very interesting fact is, and it is a surprising fact, that there are infinitely many points on the number line that cannot be represented precisely as fractions of integers. And at first this doesn't seem to make sense, because you would think that any point could be represented exactly by a fraction if you were allowed to have a big enough numerator and a big enough denominator. But it just is not so. And these numbers that cannot be represented as fractions of integers are called the irrational numbers. So these are simply defined as not rational, i.e. they cannot be represented as a fraction of two integers. Let us give some examples of irrational numbers. Perhaps, well, there are many famous numbers which are rational. One of the famous numbers is the square root of 2. The Greeks were able to prove from their geometry that the square root of 2 is irrational. And the reason that they were interested in the square root of 2 is because it arises very reasonably and naturally from considering the following problem. If I draw a square and I say that this square has length 1, side 1, then I might ask, how long is the diagonal of this square? Now the diagonal of this square is the hypotenuse of this right-angled triangle. And we can use Pythagoras' theorem, and Pythagoras' theorem is something that I speak about in one of the tutorials on trigonometry. Pythagoras' theorem states that the length of the hypotenuse is the square root of the sum of the squares of the other two sides. So we simply have to square this side, add it to the square of this side, take the square root of that, and this gives us the length of the hypotenuse. 1 squared plus 1 squared is just 1 plus 1, which is 2. And so the length of this diagonal is the square root of 2. So the square root of 2 arises very naturally in geometry. The Greeks were able to show that it cannot be expressed as a fraction of integers. It is an irrational number. In fact, nearly all of the square roots are themselves irrational. The square root of 4 would not be irrational because the square root of 4 is the square root of a number which itself is square and so is an integer. So the square root of 4 is of course just 2. But the square root of 5 is irrational, the square root of 6 is irrational, and so on. These are all irrational numbers, not the square root of 9, because that's just 3, but then as we continue, those are all irrational numbers. We will talk about these numbers in another tutorial. These are often referred to as surds. And we will talk about the arithmetic that one can do with these irrational numbers called surds. A very famous number which is irrational is the number pi. Now pi is defined as a ratio of the circumference of a circle to the diameter. Now you might think, well, then it's rational because it's a fraction. But we have to be careful. Remember, we define rational numbers as fractions of integers. The fact that pi is an irrational number means that if we consider this ratio of the circumference to the diameter, it must be that if the circumference is an integer, then the diameter cannot be. Or likewise, if the diameter is an integer, the circumference cannot be. Another famous number that is irrational is the number e. Now the number e arises when one considers exponentials and logarithms. It's not covered in the curricula at the National 5 level, but would be at the higher level. Even so, though, I think that anyone with an interest in mathematics absolutely needs to know about e. It's an extraordinary number that appears in many different places in mathematics, just as pi does. And it is irrational. Let's try to understand how to put these numbers on the number line. Well, we can't represent them as fractions of integers. What we can do is represent them as decimal numbers, decimal notation. So for example, pi is 3.141 and then ... and those digits continue forever and they never recur. There's no repeating patterns. The numbers simply continue forever. And that's true of any irrational number, that if you write it as a decimal number, the digits will continue forever and they will never repeat. But because we can write this decimal form down, we can at least represent pi on the number line. So let's see, 3.14, it would be just about there is pi. And e has the value 2.718 ... and again those digits continue forever and do not repeat. And so we see that e sits about there. And the square root of 2 that we mentioned before can be written as 1.4 4, 1, dot, dot, dot. And let's see, where would that be? Just a bit less than 3/2. So there's the square root of 2. So we see that there are all these numbers, example, all these square roots, pi, e, and infinitely many other numbers which cannot be represented as fractions of integers. These are the irrational numbers, but they are very easily represented on our number line. Now, the entire set of numbers on the number line, namely the rational numbers and the irrational numbers, together have a name. So when we take the rational and irrational numbers together, we refer to them as the set of real numbers. Now, the set of real numbers is a very, very important set of numbers in mathematics, and essentially are the numbers that one is always thinking about, in at least in the National 5 and higher curricula, when one is doing trigonometry or algebra, plotting graphs and so on and so forth. The real numbers are the numbers represented by all the points on this number line. Sometimes the real numbers are given a symbol, are the set of real numbers. I didn't mention this in the previous tutorial, but the integers that I started with are sometimes given the symbol Z, capital Z. So I think that's all we need to say about numbers for now. There are other kinds of numbers that we haven't discussed here, for example complex numbers, but you won't encounter those unless you do advanced higher maths or A-level maths or undergraduate maths, and so I won't talk about them right now, but they're such beautiful numbers I can't resist giving a tutorial on complex numbers sometime in the future. So that's numbers. I hope this has been helpful, and I will see you next time.